Hi everyone, today's topic of the video is circular motion. The goal of the video is I'll be able to apply Newton's second law to objects traveling in a circular path. Be ready for 2 secret questions I have for you some point during the video. Let's look at this lovely diagram. It shows a uniform circular motion. The word uniform means that the magnitude of the velocity of this moving object does not change, and the radius does not change, and so the path is a circle. That's what the circular motion is. The velocity of the object at every point of the circular path is tangential to the radius. It's perpendicular to the radius and tangential to the circle. That's why other names for the linear velocity are tangential and translational. For uniform circular motion, linear velocity has the same magnitude but changes its direction. So let's see what is the result of changing the direction. You may recall that there are 3 instances of acceleration when velocity decreases, right? We have negative acceleration. When velocity increases, we have positive acceleration, and when velocity changes direction. So that is finally this third case that we are learning in this chapter about circular motion. So velocity remains the same. You can see the length of the green vector is the same. However, because the direction of the vector changes, we have a change of velocity. Remember, change of velocity is by definition acceleration. Therefore, when you do vector addition, you can see that the direction of the change of velocity or acceleration is towards the center. We call this centripetal acceleration. It is always directed to the center of the circle. It also has the same direction as the centripetal force, about which we'll talk a little bit later in this video. The formula for centripetal acceleration, attention, the secret question number 1, what does centripetal mean? So center seeking is the answer, and it's translated from Latin. Centripetal means center seeking. So this is the formula that you have on your reference sheet. Linear velocity squared divided by the radius of the circle equals to the centripetal acceleration. Or the other formula you can easily derive is this, which is not given on your reference table. Every angular velocity. Okay, every point of a rotating object has the same angular velocity. So angular velocity, or Greek letter omega, which is the change of angle over change of time, is the same for every object on this line here. And it makes sense. Let's see how angular and linear velocities are connected. So every point on a rotating object has the same angular velocity but a different linear velocity. Let's think how that makes sense. So if an object is at the end of this line here, and it needs to cover a longer linear path to move around the circle, as if it were in the middle or in any other position closer to the center, which will result in a smaller circle, which means it's a smaller linear path. So it makes sense. So in order to cover it in the same amount of time, because angular velocity is the same for all the points on this line, it has to have a greater linear velocity. So relationship between linear and angular is this radius multiplied by omega. For non-uniform motion, we'll talk later. We'll talk about non-uniform motion in more detail later. I just want to touch base on this. So when magnitude of linear velocity changes, magnitude, which means the length of the vector. We're dealing with the linear acceleration, which is in this direction. At means tangential acceleration, which is the same as linear. So when the magnitude of angular velocity changes, delta omega, we have angular acceleration, which we use use a Greek letter alpha. So second secret question, alpha, some people call it fishy thing because it looks like a fish when you write it. So you need to know the answer to the second secret question, what can you call alpha? And the answer is a fishy thing. So the relationship is similar to the linear velocity and angular velocity. It's the radius multiplied by the angular acceleration. And the total linear acceleration would be found by using the Pythagorean theorem, because when you do the vector addition, and these two accelerations will be always perpendicular to each other, the centripetal acceleration and the linear acceleration, you would have just to use the Pythagorean theorem to find the total linear acceleration. Before we jump into the forces, I want to show you a reminder of how we solve problem with forces in 2 dimensions. So free body diagram, right? Net force in x direction, net force in y direction, and second Newton's law statement for each of the net forces, which is ma in each of the directions. For centripetal motion, we'll just use instead of a, we'll use the centripetal acceleration, which is linear speed squared divided by the radius. Centripetal force. Centripetal force is a resultant force. You would never show it on a free body diagram, and the cause, you would only show the cause for the centripetal force as you do for the resultant. In this case, for the ball on the rope, the cause of the centripetal force, the net force, is the force of tension. Force of tension. Example, a 5 kg bucket is spun vertically with the radius 0.7 meters. The bucket has a tangential velocity of 4 meters per second. How much tension is there in this ring at the top of its arc, the bottom of its arc, and halfway in between? And first draw a free body diagram. Tension force and force of gravity are acting down on the ball at the highest point of the circle. So net force would be a positive force, so choose the net force direction as the direction of the centripetal acceleration, which is downwards. So it's equals to the tension plus force of gravity. Also, second equation, net force in y direction is the mass times the centripetal acceleration. We combine those two, and we use centripetal acceleration velocity squared over the radius. When we combine those equations, we get the force of tension, equation for the force of tension, and when we plug in the numbers, we get the answer, which is 64.3 newtons. For the second situation, when the ball is at the lowest point in the circle, we have force of gravity acting on the ball downwards, and the tension force is upwards, which is longer than the force of gravity because the net force is towards the center, because we know that the centripetal acceleration is toward the center. And remember, the centripetal force and centripetal acceleration are directed in the same way. So we write our two equations. So in this case, tension minus force of gravity is the net force in y direction. Then we combine those two equations, and what we get is the force of tension is 164.3 newtons, which makes sense. It is greater at the bottom of the circle than on the top. For the third situation, when it's halfway in between, the force of tension is acting to the left and the force of gravity is down. So we write the net force in x direction, which is only the force of tension, and in x direction, that's what we have, the centripetal acceleration directed toward the center, and we solve for that, and as a result we have 114.3 newtons, which is in between of the top and bottom tensions, which makes total sense. Let's look at another example. A car travels at a constant speed of 15 meters per second on a level circular turn of radius 5 meters. What minimum coefficient of static friction between the tires and roadway will allow the car to make the circular turn without sliding? Does this value make sense physically? So even the car is turning at a certain point, it's not the full circle, it can be considered as a circular motion. So we have the center of the circle, we know the radius, we know the speed, which is the linear speed, which is a tangent to the circle, and we can calculate the centripetal acceleration and centripetal force. So let's look at this example right here. We have given velocity and radius, and we need to find the coefficient of static friction. So the free body diagram looks like this as viewed from behind the car. Since the turn on the picture was to the right, the force of friction is acting to the right. The gravity is downwards and normal force is upward. Let's write the net force in x direction, which is only the force of static friction, and the net force in x direction equals to the mass times the centripetal acceleration. On the other hand, force of friction equals the mu, coefficient of friction, multiplied by the normal force. And we can see that we need to find the normal force. Now we need to write the resultant in y direction, the net force in y direction, which is just the two forces, normal and the force of gravity, and there is no acceleration in y direction, therefore those two forces are equal, and we can say that the normal equals the mg. And then we can substitute it in our previous equation right here, and we can calculate the coefficient of static friction, which is square of the linear velocity divided by the radius and by the acceleration due to gravity. And after plugging in the numbers, we find that coefficient of static friction is 0.3, and it's unitless. The physical meaning, it's meaningful. It's between 0 and 1, and it makes sense. So please fill out the video. Please fill out the Google form and let me know what questions you have. Thank you for watching.